Hi everybody and welcome back. So where we ended off the part 1 series, I should call it, was the amplifier worked, but the channels were unstable. And I think I mentioned, one of the first things I mentioned was the protect relay that's in line with the speaker outputs. That just so happens to be this strange looking relay here. It's got a big coil on it, but you can see how bad those contacts are. Shame on me for not checking that, but got through all this other stuff and I just put it together and never even thought about it. So if you want to be successful in being a repair person and servicing things, you first have to come to the realization that you aren't perfect, you don't know everything, you're not better than everyone else, and you have to be willing to be patient and take the time to work through things and figure it out. It doesn't mean you're dumb or bad or anything like that. It just means that you have to have the correct attitude to work through things, even when you miss something like this. So that's what we're going to do. So let's just see what these are like. So we'll connect up to the first set of contacts and see if we can see this here. Yep. Pretty bad, huh? Really bad. And then this other one is equally as bad, and you can see it just kind of jumps all over the place. So these contacts are bad. And you know from my previous videos, I am not a very strong proponent of cleaning contacts like this. These are not the types of relays that I like to clean the contacts, because usually the tarnish is actually the plating of the contact itself that's gone bad. And when you clean that off, the base metal that's underneath it will pit and tarnish very, very quickly. So these kinds of relays, your best bet is to replace them. There are contactors that have very thick or very solid plating on the contacts, and they're quite cleanable and you can burnish them. But these are not that type. So we need to replace this relay, and we need to figure a few things out. So the first thing we want to know is, what is the DC resistance of the coil of the relay? So we're going to measure that. If my meter will hold on, there we go. And you can see it's about 830 ohms. So we want to write that down. And then the next thing we want to do is we're going to go over to the power supply, because there's no listing of this relay and there's no number that really crosses over to anything. So we don't know if this is a 12 volt, 24 volt, 48 volt, 110 volt. We don't know anything. We just know that it's a relay and it has an 800 ohm coil. So I'm going to guess what that DC resistance, we're going to have somewhere in the line of a 24 volt relay, but we have to find out for sure. So let's move over to the little power supply. Alright, I've connected the relay to the power supply, and I'm just going to slowly increase the voltage until we see the relay pull in. And there, it pulled in at about 17 volts. See that? And if we go up to 24 volts, because that's a round number, usually relays come in 12 volt, 24 volt, 48 volts, so forth. It's only drawing about 30 milliamps. So let's do a little bit of math. Okay, if we take our 24 volts times our 30 milliamps, or 0.03 amps, we get about 0.72 watts. So it draws less than 1 watt of current. That's pretty important, because the way they're using this now, some relays are driven just by a DC power supply, and it provides power and the coil just draws whatever current it needs and there's no problems. But when you're dealing with these kinds of circuits, let's get the schematic out. You can see there's a lot going on in this circuit. And I know I got a comment to keep the paper quiet when I'm talking on my videos. So, paper, don't make any noise. Don't talk. You're not allowed to talk while we're working. There you go, guys. It has been duly chastised. Anyway, you can see your relay is these two wires here. And a lot of this is going to be dependent upon not only the voltage, but the current. So the coil is actually part of the circuit. So we want to make sure we maintain that with our replacement relay. So I have this relay in stock, and it's a much better, more robust relay. You can see how big the contacts are on that. They're plated contacts. This is a Omron, so it's a good name brand. So this will work just fine. However, and it is 24 volts. However, it's going to be a little bit different. So the first thing we want to do is let's hook up our meter and measure the resistance. We want to measure DC resistance once again. So here we go. And you can see it's not 830 ohms, it's 600 and what is it? 612 ohms. So it's about 200 ohms or 220 ohms shy of the other coil, and that makes sense because look how small this coil is, look how large this coil is. There's a big difference. So, and you can see the armature and the amount of throw of this is a lot bigger than this one. And the other thing is this spring is very spongy, so this is not a really fast acting relay. This one is actually a little bit faster. But being that this is a different DC resistance, even though it's designed to operate at 24 volts, what we're going to find, if we turn our power supply back on and connect this, and we're still at 24 volts, so I'm going to turn this on, click. You can see, and the meter in this power supply isn't real accurate. It's accurate, but it doesn't, the resolution isn't that great. But you can see instead of 30 milliamps, this one draws 40 milliamps. So what does that mean to all of this? Well, what it means is that we're going to have to put in a resistor to be able to simulate 24 volts at 30 milliamps. So you remember that this one had about 830, 840 ohms on the coil DC resistance, and this one had about 610, so roughly about 220 ohms of difference. So we need a 220 ohm resistor, and if we do the math for 220 ohms, when we put our voltage drop across there, or our current through there, we want 30 milliamps. So at 220 ohms, if we want 30 milliamps, that's going to give us about a 6.6 volt drop on that resistor, and it's also going to dissipate about 0.198 watts, or just under a quarter of a watt. So if I use a resistor that's like a 3 watt, like this one, it won't get warm at all. So you might say, well, then that's going to mess the voltage up on the coil. Well, no, it isn't. It'll work as long as you have enough, the correct current and everything. And if you look here, see, it comes right in. There it is. No problem. And when I put this on, this doesn't even get warm at all. So in order to mimic this circuit and mimic this coil, we need to put this 220 ohm resistor in series with this coil, and everything will work. And I guess it would help for you to see what our current draw is. And there it is, and you can see your 300 milliamps. So there you go. The other thing I made sure of is this one pulls in at about 17.4 volts. In other words, that's the minimum voltage it needs to pull in this coil. With the dropping resistor on this one pulls in at about 16.5. So it still pulls in a little tiny bit sooner, which is fine. That's good. For this, it will work. Well, we got it to fit, and it fit in there pretty well. So there's our relay in place of where the old one was. And while I was in there, I did another modification. And I'll explain that here in a minute. But if you look, these 4 resistors, and yes, they are standing up on silicone a little bit. And I did that to space it for some heat a little bit, so it's not against the board. And that silicone is good for over 400 degrees Fahrenheit. So if those resistors get that hot, we have a lot more to worry about than the silicone. So we're ready to put this part together and give the amp another test. But let's explain this first of all. Okay, let's look at this schematic. And my wife and my grandson are upstairs, and I think my grandson's unhappy. And so if you hear him in the background, that's what it is. Sometimes I feel that way too. All right, so those resistors, let's take a look here. The paper's talking out of line again. Be quiet. All right. So if we look here, we have the Schottky diodes. There's one here and one here, and they are in parallel with these emitter degeneration resistors, and we talked about that in the last video. And what happens basically is, as long as the voltage drop across this resistor is lower than the forward voltage drop across this Schottky diode, which is very, very low, by the way, then this handles all the current. As soon as the amp starts driving any type of power into the load, the voltage drop across here rises. And as that happens, it eventually reaches the forward breakdown voltage of this, and essentially it bypasses that resistor. The problem with that is these are no longer limiting the current, and they're no longer protecting the transistors from any really nasty transients. That's a good thing as far as damping factor and the speaker is concerned that way, but it is a really nasty thing when it comes to protecting these transistors, especially when there's a difference in the current gain and so forth on the two sides. So although this can improve the sound quality, it reduces the safety factor of these transistors. Now remember, these are all in series. In order for this thing to work properly, they put this resistor in here, so at idle current there's a lot more resistance. Normally this would be, you would have these transistors in parallel, and when they're in parallel, essentially it would parallel these resistors. So the sum total of it would be more like 0.1 or 0.15 or something like that. So this is their way of working around it. Now what I did was, first of all, those MJ21193, 21194s are pretty tough transistors. So I removed these and I tested them, and all 4 of them tested different. The 2 gold ones actually tested almost like shorts, and they even had like reverse leakage on them somewhat. Not very good. These ones were probably still okay. They had a normal forward drop of maybe in that 0.2 to 0.3 volt range, maybe a little lower. These ones were crazy. They were almost zero. They're shorted for the most part, which is why the transistors probably blew out. I don't know. So what I'm going to do, what I did was I removed both of these components here, and I replaced this with a 0.1 ohm resistor. Why 0.1? Well, let's just say we had this is a 200 watt amplifier, because it is. It's rated at 200 watts per channel into 8 ohms. So let's figure we're at full power, 200 watts. Now, of course, that's not peak power and so forth, but that's continuous power. That's going to come out, if you work Ohm's law, it's going to come out to 5 amps at 40 volts into an 8 ohm load. And if we put a 0.1 ohm resistor in there, it's going to dissipate somewhere around 2.5 watts at that 200 watts. So when the amp is running at full power, there will be about 2.5 watts of energy being dissipated by that 0.1 resistor, which is half of what it's rated at. They're 5 watt resistors. So if you ran this thing at continuous 200 watts, those resistors would get really, really warm, but they would still be at only half of their rated power. I don't want to put a larger wattage resistor, because the whole purpose of them is when something goes wrong, we want them to open up. We want the resistors to do their job and blow open and hopefully protect these transistors from shorting out and going bad. It's a lot less expensive to replace a resistor than it is to replace a set of transistors. Now, another thing a viewer brought up, and I noticed this after he mentioned it, you have 3 transistors in series, and these 2 are the same. These are SAE 103s, whatever that means. And this one is an SAE 101. So technically, these 2 are the same, but this is a different one. And he mentioned that he did a repair on his amplifier. He had the same model many years ago. And he claims that one of these he thought was possibly a Darlington transistor. Now, the circuit description talks about Darlington connected transistors, but I kind of thought they meant Darlington in the aspect that the way the drivers are connected to the outputs in a Darlington configuration, but I don't know. The only thing I do know is the transistors that were in there, they were Motorola. They looked to be, I don't know if original, but at least they looked to be something that was supposed to be there. I don't know. But they were all the same transistor. All of them. They were all, in other words, all 3 NPNs were the same ones and all 3 PNPs were the same ones. So that's what I replaced it with. The amplifier seemed to work fine. I think the only place that we would see a difference if one were a Darlington would be checking these voltages here. So is it that one of these, since it's not a Darlington, are these voltages incorrect? Do I really have 50, 25, and 75 up here? Or are these voltage dividers different because one of them is supposed to be a Darlington? I don't know. We'll have to check that. I'm not sure. I'm going to test the amp and see how it works, first of all. And then if it doesn't work, we may investigate that. So that's the second modification I made on this. There is a third we're going to do later, but right now I want to put the amplifier together, test it, and see if it works as it is. We're all back together now. I'm going to put the microphone back in the back of the amplifier where the relay is, and let's turn this on. Again, we're going to put it on the dim bulb, and let's see if we got a protect relay. So here's the microphone. Hope you can hear it. So here we go. Okay, the bulb flashed and then went dim. That's good. Now let me put the next bulb in and we should get the protect relay if it's working the same as the last time. There it went. Did you hear it? Hope you heard that. Let me put the mic back on here. By the way, I do not have a button-down shirt, so I don't always put my microphone, clip it to my shirt. I put it on one of these little lanyards, and it kind of swings around and rubs on my shirt sometimes. But it's the only way I can have the microphone follow me around. The microphone that attaches to the top of the camera sounds amazing, but as soon as I move my head even the tiniest little bit away from the axis of the microphone, it gets really quiet really quick. So this mic isn't as clean sounding, and it does pick up some little rustling noise. So I was messing with you guys talking about the paper. Not trying to insult anybody, we're just having fun. You'd never make it at work with me if you can't take a little bit of jab in there. Anyway, let's since this looks normal, let's switch it to direct power. All right, and I have the signal generator on. I don't see any smoke yet. Of course, I shouldn't say that, huh? All right, let's turn it on and see what we get. All right, look at that. Totally cool. And what do we have there? That's saying 107 watts, but that's not right. It's 10.7 watts because I have the feedback, or I have the thing set on times 1 instead of times 10, the actual dummy load, the output of the dummy load. So let's connect the distortion meter. All this started with because we were supposed to check at 20 kilohertz for minimum distortion. So, all right, let's leave that 10 watts on there and let's just see what the distortion does. And this meter gets wonky like this every now and then. I don't know why, but let's turn the signal on and see what happens. There you go. Really, really low distortion. So let me turn that off. And let's go up to 20 kilohertz. Oh, it would help to go to frequency instead. Hold on. All right, 20 kilohertz, they want somewhere between 0.03 and 0.04 THD with 2.8 volts RMS into the dummy load. So we have our 2.8 volts. Let's turn it on and let's see what it says. And it's just a little bit out of spec. You can see it right now, it's saying 0.057. So it's a little bit off. So they're saying that they want the bias to be adjusted until we get the distortion down. So the good news is it's very close, and I have not even checked DC offset. I'm sure it's close, but it's probably going to need to be readjusted. So let me touch that up, and then we'll see if we need to touch up the bias at all. And I kind of want to look at the circuit a little more to see if there's a better way to adjust bias. And as you can see, bias is right pretty much where we left it. Just bouncing around a couple of millivolts here and there. So I think we're good. All right, the amp almost works. When we put a signal into it, a strong signal, you can see we have clipping there. I'm going to turn it right back off. The problem is, take a look at the power meter when we go to clipping. Yeah, it's only clipping at just under 60 watts. So what's that all mean? Or 75 watts or so. Well, the reason it's clipping is because they have the wrong transistors in there, and I have the wrong transistors in there. These two transistors here and these two transistors here are not standard transistors, they're Darlingtons. So this circuit does not have the right gain in it, and we don't have the correct voltage drops because of that. So that's why it's driving into clipping before it gets to full power. So I have to order, I have some Darlingtons, some 2N6059 and 2N6052s, but they're a little bit underrated. They might work in here, but I'm just going to order the correct ones. And I want to thank you to Bob, who is someone who worked on one of these back in the 1980s. He had one, and he kind of fell into the same trap, he said, and wanted to email me and said, hey, check I'm pretty sure that a couple of those transistors were supposed to be Darlingtons. So whoever replaced the outputs in this when this thing blew up originally, so obviously it must have in the past, put all of the same transistors in it. Namely, these old MJ15022 and MJ15023s, and that's what they put all the way across the board, when really only one of these on each side should be this transistor and all the others are Darlingtons. So I ordered the correct Darlingtons. They'll be in soon, and I have no doubt this amp's going to work perfectly once we do that. But while we're waiting, we're going to work on the one last mod I want to do on this amp. So that's what we're going to work on. But thank you once again, Bob. I really appreciate that. It was very confusing because when you look at the circuit description, it talks about Darlington transistors, but not specifically. They use some terminology like bootstrap connected, which we understand that. We have Darlington slave transistors. But it kind of, they also talk about complementary Darlington connected output transistor pairs. So, I don't know, but anyway, I looked up on my chart and lo and behold, it did cross over to a Darlington transistor. So, we're going to get those in, and I have no doubt everything's going to work perfectly once we do that. We're still going to have to set the bias, but that won't be a biggie. So another concern I had about this amplifier was this switch. This push button switch is not something that you can readily get. You very rarely see them. I wouldn't know where to get one if this one broke. And the problem with this amplifier is it's very powerful. It has a big capacitor bank and two big transformers. And every time you turn this thing on without a soft start, all it does is arc up the contacts of this switch until eventually it's going to fail. So most other amplifiers, and you've seen this in the past on the big Marantz amps that I've worked on the Sansuis, on the Pioneers, a lot of them, they put a soft start circuit. And what is a soft start circuit? Well, what a soft start circuit is a current limiting device that limits the inrush current through the amplifier while the big capacitors are charging. And then once the capacitors charge up to a certain level, the current limiting device, which is usually just a resistor, is bypassed by a relay and allows full power to the amplifier. What this does is this prevents the switch from seeing that huge inrush current and that huge arc every time you turn the amplifier on. So I decided that I was going to put one in there. Also, because I replaced the main capacitors at the power supply for the rails, I went a little bit bigger size because that's what I had in stock. So I went from a 10,000 microfarad to a 24,000 microfarad cap, and a lot of you are probably cringing and worrying, and trust me, in this instance it's not going to hurt anything, and if anything it's going to help us with dynamic power. So here's kind of what it looks like. And it's a very simple circuit. And all this is a resistor feeding the coil of a 48 volt relay. And then I have the three contacts tied together just to handle extra current. And yes, I do know that the first of the three contacts to come in will draw the heavy arc, but that's not going to be a big problem on this because there is a resistor that we added right here, this gold resistor, and that's the current limiting resistor, and it's directly in line with your mains. So what am I talking about? Well, I'll show you. So here's the schematic of the power supply, and you see your two transformers here. I will try to hold it very, very still so that you can see the schematic. And you have your positive rail and negative rail transformers, which we talked about that in an earlier video. Goes through this big bridge rectifier and then gets filtered by these two main filter capacitors here, which they were originally 10,000 at 80 volts, and we just went 24,000 at 100 volts. And that's the reason I have those in stock. Is a lot of the Pioneers, like the SX 1050 and ones like that, use those big capacitors. So, and they were exactly the same dimensions. It was an identical fit, the same capacitor, only higher capacitance. So we replaced that. The owner wanted this thing all recapped and redone so that it's finished and we don't have to mess with it. But what we did differently here is right up here where you would see this fuse. After it comes out of this fuse, we broke this line right here and we added a resistor in there. So kind of like something like this. All right, if that makes sense. Then after we added that resistor, we put our relay contacts right there. I'm drawing contacts, that's not a capacitor. Yes, it's a really crappy drawing, but there it is. So there's our relay contacts, and they're connected to the coil. And I'm just doing this. So there's your coil, and there's your little dotted line going to your contacts. Terrible Tony schematics, huh? And then this just goes out to here, and one lead goes to one side of your 75 volts, your plus 75. The other one goes through that dropping resistor, I'll show you that in a minute, and goes to the ground, or to the common point. So that's what it is. And if you look here, that's all we've done. So here's your common point coming out and goes to this resistor. This is the dropping resistor. And basically what I did was I took the 75 volts. This thing draws 30 milliamps when it's pulled in. So it's a 30 milliamp coil at 48 volts. So if we know we have 75 volts across this capacitor, or this one actually, because you can see here's the other wire coming off right here, and it goes over to here. This is the coil. So at 75 volts minus the 48 volts, we know what voltage drop we have, and we know that we need it to be at 30 milliamps. So if you take the 30 milliamps plus the voltage drop on there, you can use Ohm's law and you'll calculate the resistance, and it comes out to somewhere around 900 ohms, give or take, either 870, something like that. It's somewhere around 900 ohms. These are 470 ohm resistors. So that's going to be about 940 ohms, which is right around where we want to be. And these are nice metal film capacitors. So, and they're each rated, I think, at 5 watts. So they're way overkill. They'll never get warm or anything like that. So essentially what's going to happen is, as these capacitors charge up, when you first turn the power on, they're charging through this resistor. So let's come back here. So that's going to, because see, here's your mains coming in. It's going to go through this resistor because these contacts are open right now. And that resistor, which is 10 ohms, okay, actually it's a 15 ohm, 15 ohms at 25 watts, that is going to limit the inrush current to these transformers. Because you see the transformers are just kind of looped in there. And as this charges up, it's going to kind of slow down its charge rate. Once this hits the trip point of this relay will pull in. Now, a 48 volt relay will pull in at somewhere after 30 volts. So what that means is this capacitor does not have to be fully charged for this to pull in. Only maybe about 75–80% charged, at which point it's safe, because now the remaining charge of the capacitor isn't going to be that bad. This pulls in, it shorts between these two wires, so it shorts out, coming back here, it shorts out this relay contact, and essentially you just have a straight wire through here, through the relay contacts. So all that's doing is limiting the current. So now that we have a soft start circuit, it's okay to use these bigger capacitors, and we have extra headroom in case we have a big bass passage or something. Hopefully it will help with that a little bit. And that's all there is to it. So, very simple circuit. I have one last thing I'm going to do, one last mod that I think I'm going to do, and a couple of you suggested it. It was a fantastic idea, and therefore I'm going to go ahead and do it. If you remember on the previous video, we were reading the circuit description, and we were also reading some of the notes on the repair hints. Let me grab that real quick for you. And let's go back to the repair hints. And it said down here, it was talking about the wide bandwidth of the amplifier and 200 kilohertz. This is unacceptable. I mean, how many people may knock the plug loose, their RCA plugs from the preamp loose, and the amplifier buzzes? If that's enough to send this into a catastrophic failure, to me, the design is a failure. I don't want that to be like that. So we're going to make a little change to this that will hopefully help with that. And all of these things may trade a little bit of sound for stability, but I would argue that almost everyone would not hear any difference. And even those who could hear a difference could only hear a difference under the right circumstances, with the right speakers, with the right listening room, and so forth. So I think this is going to be a lot better trade-off to make the amp more stable and not worry about the crazy, back when this amp was popular, when it was being built, there was this big thing about having fast amplifiers and talking about the transient intermodulation distortion and all these things like that. And everybody wanted to tout how high frequency, and I showed when I did that Sansui AUX1 how ridiculous it got. It got to a point where I actually was able to feed a 1 megahertz signal clean with no problem through that amplifier, connected to a little wire, the speaker terminals, and I was able to transmit on 1 megahertz onto an AM radio. That's craziness, you know what I mean? So we're going to tone this down a little bit, and we're going to put a filter on the input that's going to prevent, hopefully, that problem. Now I got another message, it was a comment on that last video. It came in either this morning or yesterday, and he was talking about that low pass input filter, and he had mentioned that he had read about this in this book, and this is one of 2 amplifier books that I think are just a must if you're going to get into this type of work. This one for solid state amplifiers is the way to go. It's by Bob Cordell. He's very well known in the industry. I think anybody that does audio electronics knows this book. This is kind of the de facto reference for this, and it's called Designing Audio Power Amplifiers by Bob Cordell, and this is his 2nd edition. The 1st edition was super duper popular. And if you go over to at the beginning, when you get into chapter 4, he talks about these front-end low-pass filters and talking about the input network. And essentially what it consists of is a 68 ohm resistor, which is a compromise between 50 ohm and 75 ohm. Shielded cable is typically will have an impedance of 50 ohm or 75 ohm, and that's too much to get into on this video, but essentially this is kind of a compromise between the two, like it says, and a resistor and capacitor network. And if we go to the next page, and here I'll stop, if you want to kind of pause the video to read that, you can. And if we move over to the next page, you will see what everybody's talking about, this little network here. And what he's talking about is this 68 ohm resistor and this little RC network right here. And it's before the input of your differential. So on our amplifier right now, I'll show you. Let's see, grab the schematic for it, which is under a bunch of stuff. You guys getting dizzy that because I'm moving the schematics around? All right. So here we go. You can see there's just a resistor. It's a 1K. Goes straight in. Here's your capacitor, your coupling capacitor, and it goes straight into your differential pair. And if you notice the difference between this and this, you see what we have here? So this is what we're going to add. Hopefully this will help a little bit with that input stability, I hope. We'll see. So here's our low pass filter mod, and you know, we say low pass filter, that means just because it says low pass doesn't mean audio low pass. That means it's filtering out high frequencies up in that 200 kilohertz range that they're talking about, and below a little bit. But right there is your 100 picofarad capacitor. And if you slide this little thing back here, you can see there's your 68 ohm resistor. And all the other components, for the most part, are already in the circuit. You still have the 1K resistor. You still have the capacitor, you know, your coupling capacitor between the differential input and so forth. So if we go back down here and we look at the input stage, there it is. So that 1 meg was already in there. So we just shunted that 100 picofarad right there. Your 1K is right here, and we just put the 68 ohm right there. And that's really as simple as that. That 100 picofarad capacitor that we put across there, that little blue one you saw, is going to shunt out any RF noise. It'll just shunt it straight to ground. And the audio will still pass through with no problems at all. And like a couple of the viewers mentioned, who knows why they failed to put that in there. So the amp is finished, and I still have to wait until tomorrow for the Darlington transistors to come in. And as I said earlier, I don't know how the original owner of this amp that sold it, how he could have said this thing worked perfectly, because the transistors obviously have been replaced, and they were replaced with the wrong ones. 4 or 8 of the 12 transistors were supposed to be Darlingtons, and somebody had replaced them with standard transistors. So that was kind of a lesson learned right there. So you can't even rely on looking at the old component in an amplifier and finding a substitute and replacing it, because if somebody worked on it before you, they may have put the wrong components in. So there's a lesson learned from this repair here. So I'm sure when we get those in, though, this thing's going to work great. I'm zoomed in as tightly as I can possibly get without going out of focus. And I want you to kind of look, we're all going to look right down here where I'm pointing, right there. See, those are the contacts. You should see them close. Once we turn this thing on, after a short delay, you should see that close, and you should see, which will bring in full power, and that's the soft start circuit. So if all's working well, that's what should happen. Here we go. 3, 2, 1. And there it went. And there went the protect relay. So there you go, one after the other. And that's exactly how this should work. And if we shut the power off, once the caps drain down, the relay will drop back out. there it went. And so that's pretty much how it works. Alright, I hope the lighting is good on this thing. The Darlington transistors came in today, and I'm getting ready to replace them. And you can see I have the MJ 21193s and 21194s in there. And I have everything put in exactly the way that the old transistors were in there when I took them out. I very carefully documented everything. And they had them alternating. Every other transistor was NPN, PNP, NPN, PNP, all the way across. I thought that was kind of strange. So I thought I would do a little more checking, and it was kind of a chore to kind of cross everything over. But I printed out the layout of the board that came with the service manual. And sure enough, not only did they put the wrong transistors in 8 of the 12 positions, they also put the polarity of the transistors in the wrong places. So the correct way this should be, and I checked all these traces. I actually matched the traces up with the components and the schematic. And if you notice, all these 3 on this side are PNP, all these 3 on this side are NPN. This is the one channel. Then when you move over to the other channel, all these transistors on this side are NPN, all these ones are PNP. And the ones I marked in orange and green are the Darlington transistors. And I'll try to remember to put a little image up on the screen here explaining, for those of you who do not know what a Darlington transistor is, a little picture of one and a little description. It's basically 2 transistors wired together with the emitter of the first transistor connected to the base of the second transistor. But maybe I'll cut something and paste out of Wikipedia or something so you can see quickly what it is. Anyway, so not only do we have the wrong transistors, they're in the wrong place. So again, you know, when I got this thing, the person who bought it said that who he purchased it off of had it connected, and he played it, and they were listening to it until the smoke came out and it stopped working. So as you could see, even with it totally miswired, there was enough to get about 50 watts per channel before it started clipping, even with the wrong transistors in the wrong place. What are the odds of that? And the only thing I can figure is whoever worked on this before me must not have had the proper service documentation and must not have known. They must have taken all the transistors out and then forgot where they went when they put the new ones in. So it's really amazing that this thing just didn't completely burn up the traces on the board and burn everything up. I mean, it just amazes me that this thing survived in as good of condition as it did. Luckily for us, it did. So anyway, I'm going to remove the transistors. I'm going to replace the ones that are wrong with the correct ones, and I'm going to switch around the ones so they're in the correct position. And as soon as I do that, we'll take another view of it to see what it looks like when it's put together right. Okay, we now have the proper transistors in the proper position. So let's see if it works. Alright, the amp is connected up. I don't have anything on the speaker terminals other than my voltmeter set to millivolts mode. And it's just going to read a bunch of noise right now until the protect relay pulls in. You're just going to read noise. So I won't look at that yet, but I have the first bulb, which is this little 40 watt one on the current limiter. That's it. And we're going to turn the power on, and we're going to see if it dims down. If it dims down, that means that the transistors at least are not shorting. So let's try it. And it is dimming down. Very nice. Now that bulb is limiting so much that it's not even allowing the capacitors to charge up far enough for our soft start circuit to kick in. So let's bring in our next bulb, and we should hear at least the soft start circuit kick in. We may even hear the protect relay kicking in. So we may hear 2 clicks. So here's the bulb. 1 click, 2 clicks. There you go. So now the amplifier is turned on and it has come out of protect mode. So that means it's happy. And looking over at our 2 meters, these meters again are in millivolt mode, not volts, but millivolts. And you can see the left channel has about 8 millivolts negative, and this one has about negative 6 millivolts. So that's not too bad. Remember, we still have the original settings from when the amplifier had the wrong transistors in the wrong positions. And believe it or not, just because a couple of them were in the correct position, the amplifier actually somewhat worked. But remember, it clipped at about 50 watts. Alright, so let's adjust this and see if the DC offset adjusts, which tells us that the transistors are active. So, okay, I'm sorry, this is left channel, this is right channel. I have them backwards. See if I'm going the right way here. Looks like I am. Or not. You'll 50-50-90 rule. If there's a 50-50 chance you'll turn the pot the wrong way, 90% of the time you'll pick the wrong 50%. It's working. Believe it or not, it is working. And you can see there's negative 1 millivolt. Let's try the other channel and see if it works. See if we can do something with it. Oh yeah. If you notice, you adjust it and it jumps and then it resettles as the transistors adjust to the change in the voltage there. I don't know. I think looks okay to me. I think we're ready to try this thing out. Alright, now I'm going to just leave this meter on because it's got a nice big display on it, and we're just going to check that bias for that 2.1 volts again. And I don't know if it's going to be negative or positive because I might have these probes on here backwards. But on the right channel, 2.35, and it's supposed to be 2.1, so it's a little bit high. So we could turn that bias down a little bit. And this one over here, 2.1, 2.14. So that's a little bit closer. Now that might be different now because if you remember, we removed those 0.39 emitter resistors and we replaced them with 0.1 ohm emitter resistors. So that may change all of that for the idle current and so forth. So what we will do is we will reduce the bias on this thing, and then we will check, like they recommend, we will check at a very low amplitude, low power output at 20 kilohertz, and we'll try to get minimum distortion. But before we do that, I want to make sure this amp is stable enough to run on full power. It's almost there now. We have 102 volts and we're drawing about 535 milliamps. If I switch the third big bulb in, the filaments are almost completely out now because you can see there's almost no glow at all to the filaments. Very, very low. And you can see up there about 700 milliamps and 113 volts going into there. So that's close to full power, and the amplifier seems to be just purring right along here with no problem at all. These are staying nice and cool, and heatsink here, nice ice cold. So I think we can try, let's dare to put it on to full power. If this thing's going to blow up, it needs to do it now so that it doesn't do it in front of the owner when they get it back. So here we go to full power. And what do you know? It looks good. Nice. Okay, let's turn it off. Let's wait for our relays to drop out. Okay, there, that one just dropped out. You notice how long it took for these capacitors to discharge through the coil here. So a lot of capacity in these caps. These are 24,000 microfarads each. Now let's turn it on and let's just see how fast, after we turn it on, how fast the relay comes in, the soft start. Because remember, it comes in when these caps are charged about 80% or so. So I'm going to hit this here, and we're going to, I'll try to get it so you can see. Let's see if we can zoom in back on those contacts again. You should be able to see it right there. And you'll see that contact move. So right in there is the contacts. You can see them. Okay, ready? Turning it on in 3, 2, 1. Very quick. Do you see how fast? So about a half a second or so. And that's really all it takes to get through that inrush current, is about a half of a second. And during that half second, that gold resistor there, you can see, is actually limiting the inrush current. So our soft start circuit works. Okay, let me get some speakers and a signal generator connected to this, and I'll be right back. Okay, amplifier is on, and I have a 100 millivolt signal going into the terminals of the amp, and we're going to turn it on right now, the signal generator. And the noise and triggering problem is because I have this set to 200 millivolts per division, so it's just kind of false triggering on the trigger. But if you look, we're getting a pretty clean looking signal. Okay, so now let's go up to 300 millivolts, and we're going to have to change our volts per division. I'm going to go to 500 millivolts per division. And there you go. And let's see how many watts that is. That's about 7 watts per channel right now. And total harmonic distortion, 0.005. So far so good. All right. Let's go to 600 millivolts. Just move it up 300 millivolts here. So 600 millivolts in. Yeah, better change my volts per division again. Go back to 1 volt per. All right. Okay, here we go. And harmonic distortion is 0.006. And we're getting 29 watts per channel. Looking good. Do we dare? Let's go up to 1 volt. So I'm putting 1 volt RMS into the input of the amplifier. I'm going to have to change my volts per division again. All right. And let's see how many watts we get out of this. Can definitely hear the amp whining. 81 watts. THD 0.006 still. Nice. Okay, and we're about halfway there now. So let's go to 1.3. I don't know if I should drive this thing much harder now. Okay, one heatsink, or one side of the heatsink, so if we look over here, after running that 86 watts, this side is warm to the touch. not hot, it's just warm to the touch. This side is still almost ice cold. I mean, it's room temperature. And if you remember, this was the side that was reading a little bit high on the bias. So I think before we go any further with this, we should adjust our bias. We know the amp works and we know it's running clean now. So we're going to flip this up on its side and see what we can do about the bias. Alright, looking at the underbelly of the amp, I don't even know if you can see it from here, but if I zoom you in close enough, I think you can somewhat see there is a tiny little potentiometer hidden right here in this slot. And it has I don't know if we can get the light on it at an angle that you could see. There you go. Right there, see? Can you see it? Right there. That little knurled knob. That's the actual bias pot right there. Very, very hard to get to, but I think we can get in there with something and just like with this little screwdriver and just grab that knurling and adjust it. That's the way you have to adjust this thing. And the other one is down here below for the other channel. It's right here. Can you see it somewhat? I don't know if you can get it at an angle enough to see. There it is. You can kind of see it right there, that green thing. So I'm going to reposition this amp, and I'm going to get my meter connected, and I'm going to try to adjust that upper channel so that I'm going to go to 2 volts. And the reason I'm going to go to 2 volts once again is because of the different sized emitter resistors that I have in there. We really don't care if the bias is set low. The only thing we care about is if the bias is too low, you'll get crossover distortion at low volumes. That's why they have you go to 20 kilohertz and very low wattage, like, you know, only a couple of watts of output power, because that's when you're going to see the biggest influence of bias being too low. So that's what we're going to do. We're just going to set the voltage, just do a static adjustment, 2 volts, and then we're going to retest the amp. Okay, I have this one turned down. I'm going to move over to the other test point, and I'll do this other one. I'll let you see me adjust it. So let me move the camera around, and let me move the probes to the other test point, and then I'll be right back. Alright, I hope you can see all this. It's hard to get the reflections and all that, but let's move this down. So we're at 2.16, so I'm going to move this way, and you have to let it stabilize after you adjust it. It doesn't move right away. You have to move the pot. Okay, and you can see we jumped a little too far. Turn it back up. It's kind of awkward. It's hard to move it without like moving it real fast. There we go, 1.97. That's pretty close to the other side. I'm going to leave these at that. And we're going to redo our test, and I just want to make sure that this thing doesn't overheat. Okay, looking at the specification, they want somewhere between 0.03 and 0.04% total harmonic distortion with 20 kilohertz into an 8 ohm load at 1 watt, which is 2.8 volts RMS. So let's see if we have that. I have it dialed in, and I need to change my scope to measure lower ranges like that. And I don't know, let me switch this over to ×1, and let's see what we can do here. There we go. And this is 10 times what it should be, so it's 1 watt. It's saying it's 100 watts, but it's 1 watt actually. Ignore that because I have the scaling set different on my dummy load. And look at that. They want it to be between 0.03 and 0.04, and it's 0.029. So we are well within specs. So I think we have achieved success. So let's set this amp back down the right way, and now we're ready to do some tests. Okay, after you run this thing for a little while, the protect relay comes in, and the power meter on the left channel here indicates power, which means there's a DC offset, high DC offset. So what that's telling me is one of these transistors on this side here is going crazy. So I think one of our transistors, and it could be either these 6 drivers here, or it could be these, anything in here it could be. One of the transistors, I think, is noisy or whatever, is going bad. So we're going to have to do a little bit of troubleshooting. So look at this meter here when it comes on, and hopefully it'll do it. And you can see right now there's it's showing 2 watts. I don't know if you could see that straight on, but that's DC offset. And if you look on this meter, it's all the way down on 0, which the protect relay is not coming in now. It's dropped out. So it's in protect right now, rightfully so. So what that's telling me is there is a transistor over here that is failing. Those 6 here, these 3 and these 3, and these 2 transistors here and here are the only 2 that I did not replace. Now, possibly one of my transistors may have failed. I highly doubt that these ones would have had a problem, because they're rated at a much higher voltage and current rating than the original ones, so I don't think they're a problem, and they have the same gain characteristics and everything. These up here, very similar, but again, there could be a problem with them. So we're going to look and take a few measurements and see if there's a voltage that's not where it's supposed to be. Well, now, show me where you've been and I'll show you where the problem is. So first of all, when I reconnected these meter wires to the metering circuit, I got them reversed. So even though this meter was showing that this channel was the one that had the DC offset, it was actually this channel, because the wires are swapped. So I need to take the leads off of here and swap them with here, back and forth. So that'll fix that. But, sorry I didn't have my coffee yet this morning. But more importantly, I don't know if we can focus in on this. There it is. Can you see what I see? I don't know if you do, but if you look right in between these 2 pins, there's a tiny little strand of solder in there. Let's see if we can remove that with something. And there it is. Let's see if we can pick it up. Don't know if you can see that, but there it is. Let's see if it works now. Alright, let's check our frequency response at about 25 watts. I'm not going to run this thing real hard. And I do have both channels, and I'll show you that. You can see the blue channel is kind of hiding underneath there. So if there's any anomalies from right to left channel, you'll see the blue kind of poking up above or below the yellow channel. So here we go. I'm going from about 10 hertz up to 20 kilohertz. And it's holding amplitude very well. And the 2 channels are staying right on top of one another. Nice. Perfect. All right. One thing I noticed from working with this amplifier is it needs between 5 and 10 seconds to stabilize after you turn it on. And the funny thing is, the protect relay will pull in before the amplifier is actually ready. In other words, there's no DC on the terminal, so of course the protect relay comes in like it's supposed to, but the amplifier still isn't totally stabilized all the way through. And if you hit it with a real fast transient at that point, it'll trip the protect relay, then it'll pop back on a couple seconds later and everything's fine. If you wait about 5 or 10 seconds after you turn the amp on, that doesn't happen and it works perfectly. And I think that's just, again, one of the properties of this amplifier. And the protect circuit is very sensitive on this thing, which is good. So it does monitor the output. So here's 20 hertz. And you really can't see it because, there we go. And here's our THD. So it's 0.0, bouncing around 0.02, something like that, at 20 hertz. And you can see right there, 20 hertz. All right, we checked 1 kilohertz earlier. We're going to check 10 kilohertz now. And that's really nice. So there's 10 kilohertz. And there's our THD. Not bad. And last but not least, let's go for 20 kilohertz. We already did that, and we kind of know where it is, but we're going to do 20 kilohertz at about 20 watts now. So we tried it at 2 watts. We're going to try it at 20 watts and see what our distortion looks like. So there we go. And 20 kilohertz. And distortion looks great. So the amplifier is working, I think, how it's expected to work. And just to check that we don't have any kind of ringing or any kind of oscillation, we have 1 kilohertz square wave, and that looks pretty good. I don't like to run square waves for a really long time on an amplifier. That's tough on the Zabel network and things like that, but we just want to make sure there's no problems. And you could add capacitive loads and so forth, like to simulate a speaker with a crossover, and we could see if we could get it to oscillate, but I highly doubt it because this has some pretty good filter networks on it. Okay, I don't want to kill this thing, but we're going to drive it at near full output, which is 200 watts. We're going to give it long enough for the power wattage calculation to take place, which is about 5 seconds or so, and we're just going to see how it holds. Here we go. Distortion is 0.01, and you have 181 watts, as you saw there. Let's go one more click, see if we can get it up to 200, because this is a 200 watt amp. It should do it before it clips. Look at that. Clean as can be. 205. There it is. 205 watts. All right. Let's see if we can get it to clip. There it goes. And it's clipping off at about 225 watts. And it's very symmetrical clipping. And by the way, the two channels are once again on top of one another, so whatever that yellow channel was doing, the blue channel was doing as well. So this amp is performing very well. And I'm just grabbing the heat sink now. Let's go down and look at that. And I'll be honest, it's warm. It's warm, not hot at all. Very good. The drivers, just warm. and they all just feeling, you know, you can't tell totally by your fingers, but they feel pretty equal in temperature. I was checking down here. I just realized I was off camera, but over here and here and here. Nice. Very nice. I think we have a good amplifier. Well, that was a little bit of work, but here we are. Looks good. Okay, let's do a little test here. So I have something I've not tried before. I have my Zoom microphone. Let me come up here. AKA the Imperial Walker. And I have it set to record right now, but I'm coming out of the line out and I'm feeding it through this wire directly into the camera. And of course, the record level's low right now because I have it set for the stereo. And what I'm going to do is I'm going to shut the air conditioning fan off and everything, and we're going to go ahead and try this out and see how it sounds and do a test song. Alright, so let me get that set up and we'll be right back. Okay, hopefully this will work. Let's see what it does. Well, I have no idea how that turned out, and because I've never tried this before, but we'll see when we get it edited. But anyway, I think that wraps this one up. So what all did we do? Well, we replaced, of course, the bad transistors. We recapped it. We put the correct Darlington transistors in there. We replaced the protect relay with a new one, a better one. We modified the emitter resistor setup, and we removed these 0.39 resistors along with these shorted out Schottky diodes, and we replaced them with 0.1 ohm emitter resistors. We biased and DC balanced the amplifier. We also changed it to a 15-turn pot for the DC balance. We replaced the the power supply filter capacitors, the big ones, with 24,000 microfarad 100 volt caps. And we added a soft start circuit, and we also added an input RF suppression network to limit the RF frequencies from getting into the input of the amplifier. And we made sure that any of the small signal transistors that looked bad or unmatched or whatever got replaced with matched pairs as well. So with all that, it worked out really well. It sounds good. I can tell you this is one of the loudest amplifiers, either 200 watts or not. This is so unbelievably loud. I just couldn't believe it. I think whoever ends up owning this is going to have a good amplifier though. So I am not done with the SAE product line. I have 4 more products I can do. The one that's going to come up next is going to be another SAE, but we'll wait till the next video to see what that is. And until that time, I'm going to wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon. Take care. Bye-bye.